Good morning to all of you. Today we'll discuss the benefits of FACTS technology and we'll compare with this HVDC and other controllable parameters. Already we have discussed in power flow, that also we'll discuss. Mainly we discuss the benefits of FACTS technology. See, these are the topics. Already 3 topics we have covered in the unit 1, that is the basics of power flow in AC system, and then loading capacity of a transmission line, and basic types of FACTS controllers we have seen. Again, we go back and discuss about different topics briefly, and we'll move to the importance of controllable parameters and the benefits of FACTS technology. Of course, dynamics stability conservations we have discussed in the power flow itself. Again, we'll discuss. See, the power flow in AC, okay, simple AC systems, if you consider, it has sending end bus and then transmission system, then receiving end bus. This is the simple power system. You can connect here the load, or you can connect any other bus or generator you can connect. Once you connect it as a generator, then you can consider it as a 2-bus system, 2-bus machine. Okay, a 2-machine system. Here we consider it as a 2-machine system, where we consider it as a first one as a sending end and second one as the receiving end. We can consider here load also. So that is a SMIB, a single machine connected to infinite bus bar. This is the simple power system where you can analyze the stability and everything. That is infinite bus bar. Means the voltage almost constant irrespective of the generators loads added to that one. So that is the single machine connected to the infinite bus bar. If you consider load at the receiving end, or if you consider one more generator, okay, with the different loads, you will have loads at the different buses also. Don't think that only 2 generators are connected. So you will have a load also here at this point. Okay, see that you can consider it's a 2-machine theory. Here we have already considered the lossless transmission line and calculated both real and reactive power. So mainly we consider real power because that is useful in the power system, but whereas the other reactive power, we require that okay, in a power system for some of the components or devices or equipment like induction machine, transformer, inductive type of loads, whatever it may be. So we require a reactive power. Without that, they won't function. So that's why in a power system, we require both real power that is actually useful and also the reactive power. But actual thing which is doing the work is nothing but the real power. So we have calculated real power in this single machine connected to the infinite bus bar or 2-machine theory. So in this case, the real power at the sending end and receiving end both are same, given by V1 V2 by X into sine delta. So you have to consider here different parameters. So that is X, delta, and also how these voltages will change once a shunt compensator is considered. Because so already we have discussed about this equation. Again, I am repeating this because entire thing, power flow control is possible by controlling any of the parameters in this equation. That is either X value or delta value or by controlling the voltage. Okay, how we control the voltage means by injecting the voltage so that you can control the potential difference or the voltages. Okay, so that way you can control the real power flow through the transmission system. Actually, how the power is controlled exactly, that we'll discuss later sections. Here, so main basics of power flow in AC system you have to know. So this is about real power, and similar to this one, we can calculate reactive power that mostly depends on the voltages. For example, at this one, if you calculate, that is simply V1 into V1 minus cos V2 cos alpha divided by x value you are considering, cos alpha divided by x value you are considering. So here, once you consider this second term, q is proportional to v square by x, so that any particular node, the reactive power is directly proportional to square of the voltage. So by controlling the voltage, we can control the reactive power. Of course, x is also has impact on the reactive power, not only the active power but also on the reactive power. Okay, you can see that this equation. Okay, see, so that is about simple basics of power flow in case of AC. Okay, here again coming to the second point, loading capacity of the transmission line. Assume that this is the transmission line. Okay, we are assuming this transmission line. This has certain capacity. We cannot exceed that capacity. Okay, power flow. Each transmission line will have certain capacity. You can see in terms of power, kVA or MVA, or even in terms of current also you can say, because the voltage is almost constant, we can consider, so that there is a limit on either current or power we are considering. Uh, Apparent power or even real power limit also we can consider. kVA limit will be there generally for any transmission line. So generally that limit, that capacity of the transmission line depends on three factors. This is depends on three factors. One is thermal capacity, thermal conditions. Second one is dielectric capacity or the voltage limits. Third one is the stability considerations. In the case of thermal, means particularly the physical, that is temperature, ambient temperature, and then ground clearance, and other factors will be there in the case of loading capacity. So transmission line capacity, physical, mostly the physical parameters. Okay, ground clearance, sag, all other, okay, distance between towers and whatever it may be. Okay, that we consider in the case, and of course the thermal, mainly thermal means temperature, ambient temperature you are considering in the case of loading limits. Then the most of the cases that we consider the temperature. And coming to the second one, that is important, every every machine or every line, every wire generally will have certain capacity, that is the insulating capacity, the dielectric capacity or strength. If generally that depends on the voltage. If voltage exceeds that actual voltage, then insulation damage will occur to the that particular machine or wire or whatever it may be. So for even for the transmission lines also having certain limit, voltage limit. Okay, even if it exceeds by 10%, 10% don't have any effect. It can bear that voltage. So here in the case of transmission line, the dielectric capacity, that is the limit depends on dielectric capacity. Again, that dielectric capacity of that one depends on the voltage. If it can bear 10% extra voltage, over and above 10% gives rise to a problem insulation damage, so that you have to limit the line capacity by certain value based on the dielectric capacity or strength. Then coming to the third one, that is very important, stability considerations you have to take in this one. Okay, number of stabilities are there: steady state stability, transient stability, and dynamic state stability. Your dynamic stability you are considering in all these three, the magnitude of the fault or problem is different, and the analysis is also different. In particular, we concentrate generally either steady state and or transient stability. Transient stability analysis is very important even for a single machine or two machine theory or power for a power system. Okay, how it will react to a particular sudden change of uh, system. That is, when a line to ground fault occur in a double circuit line, you immediately, if it is cleared within a certain time, whether it comes to stable or not, okay, that analysis is required. So in the case of transient stability, we are analyzing the system behavior even during the faulty conditions also. So one of the example that we are considering or analyzing the transient stability is that the study, the swing, this equilibrium criteria. So that swing from the swing equation, you will get a number of methods are also there to solve that swing equation. We solve that by using equilibrium criteria. We formulate, okay, we take, okay, in the equilibrium criteria, we take power along the x-axis, mechanical power, electrical power, we consider, and fault condition, and how this power, we are assuming that mechanical or uh, turbine power is constant, and electrical power will vary with the delta as given by the above equation. So the from the swing equation, when there is no problem or steady state condition, the swing will be zero, or the mechanical power is equal to electrical power, or whatever the power that is the machine is getting from the mechanical side, that is turbine, same will be transferred to the electrical side. So mechanical power is equal to the electrical power, there won't be any disturbance. Once fault occurs, then this example line to ground fault occur, or when it is connected to ground, the entire electrical power will be zero. Only mechanical power will be there, so that the machine will swing because it takes the mechanical power. So that speed increases. The accelerate machine is accelerating, and then once it is cleared, and again decelerating acceleration, and again whether it comes to stable or not, that we'll discuss. Okay, and that depends on the critical clearing angle, at what time you are clearing the fault. Many things we study later. Okay, for example, if you clear the fault at this point, okay, mm, at this point, okay, the later we'll discuss different analysis. Okay, uh, mm, we calculate the areas and normal condition. That is when before fault occur, and the swings we consider along the equilibrium point, whether it comes to the stable point or not. We'll discuss further later. Okay, in the later sections. Okay, and stability limit will be there. Okay, stability limit. For example, if you are allowing the machine to swing up to a large value, okay, that is, if you allow the motor to or assume that at this point you are clearing, so that this area we are considering the area electrical, the area under the curve, that is P minus P minus PM, and here, and when the areas are equal, then you can say that marginally stable. When this electrical area is this one, or this one is greater than this, okay, then this, okay, this decelerating area. This later we'll discuss for other points. Okay, this is called steady state limit. Sorry, transient stability limit. The extra one we have so that you can enhance using this uh, mm, facts controllers. This further study we analyze in the last, that is the shunt compensator or series compensator, while discussing the objectives. That is different. So the loading capacity mainly depends on the stability considerations, dielectric strength, and also the temperature. That is the thermal capacity of the transmission line. And again, different parameters, stabilities, you can voltage stability, and also frequency collapse. That is the reactive power control, and frequency collapse is the frequency stability. Also, you have to see voltage stability. Also, you have to see, and also subsynchronous resonance. That is the a separate condition problem you can get in the case of series compensator, that also to be addressed in this one. Okay, then that is about different loading, about loading capacity and other. Then okay, see, coming to the different types of facts controllers. Last class we have discussed about different facts controllers. Assume that this is the sending end. We consider a simple box. Thyristor box is considered as a facts controller. Okay, so this one. Okay, this one is the facts controller we are assuming. Once it is connected in series with the a transmission line, then we call it as a series facts controller. Once it is connected at a particular node, you can see that in shunt, for example, if you consider this as a facts controller, okay, then it is connected at a particular node at a particular point or across that line, transmission line. So then that is called as a shunt compensator, series compensator. And in the these are the main two. And in addition to these two, you will have one more, that is the two more you have, that is series facts controller. We are assuming multiple series lines. Okay, and there we consider two facts controllers, series combination of series you can consider here. The DC supply, the DC terminals of these two generally will be connected. Then that is called as a interline power flow control, and this box you can consider it as a converter. Converter. In case of simple one, series combination of a series converter you will have. That is combined series converter you will have. Then in some cases where you will have series facts controller and also shunt facts controllers. Okay, so that is a combination of series shunt. Okay, series, and this is the classification regarding facts or controller. That is series facts controller, shunt facts controllers, series combined series facts controllers, combined series and shunt facts controllers. These are the this is the basic classification regarding facts are considered. Then based on the generations, actually in the case of general technology, we can say that 2G, 3G, 4G, and 5G is also coming nowadays. Okay, the new technologies introduced in the mobile technology based on the bandwidth of the downloading capacity and other. Okay, based on that, we are classifying the generations. Okay, similarly here the first generation facts controllers generally will have a simple electronic switch and a capacitor or an inductor to control the either reactive power or active power, either in series or shunt. Examples are there: thyristor controlled reactor, that is shunt compensator, or thyristor switched series capacitors. You will have TSC or TSR, like that. Okay, switched capacitors or thyristor control reactors, like that. Many we have series and shunt facts controls. One that is a switching device you will have, plus in addition to that, will have either inductor or a capacitor to compensate or to control the power. So that is about first generation FACTS controllers. And then coming to the second generation FACTS controllers, there we use voltage converters or current source converters, VSC or ISC we use. So that is the advanced we can compare when consider the simple power switching device like thyristor. Converters you will have single phase or three phase. It will have controllers. Generally, once you consider even this single TCR or TSCs or whatever maybe you are considering, it has a controller. Without controllers, it is because you have to design the firing circuit even for this one simple one first generation FACTS controllers also. So in the case of even the second generation FACTS controllers, that is converters, there also we using the converters with the controllers, voltage source converters or current source converters plus controllers we are using. These controllers are used to sense the different conditions, that is real power, reactive power, currents or voltages, and based on that we design the firing circuit required for these converters. So that is the purpose of control circuits used in the second generation FACTS controllers. So we use only one controllers in the case of second generation FACTS controllers. In the case of 3G, third generation FACTS controllers, there we use two converters. Okay, series converters. In both the cases, we can use converters or combinations of series shunt converter. Also, we can use these two converters. So that we can take it as the advanced technology. So third generation FACTS controllers, we are assuming in that case two converters we use, series converter or series shunt converters. Again here in this we are considering two important devices. One is UPFC, that is Unified Power Flow Controller, UPFC. In that UPFC, you will have two converters, one in series and other in parallel. Okay, that is unified. Why we call it as a unified power flow controller? Generally, in this case of series shunt controllers, the DC terminals will be, for converter generally will have DC side and AC side. Generally, AC side is connected to the transmission system because the transmission, whatever maybe you are assuming it as AC. So AC side of the converter generally connected to the transmission system. Then the DC side of either series converter and the shunt converter, that is connected. Then that is called as a unified controller, whether it is a series controller or a series shunt controller. We can unified power flow controller is a combination of series shunt controllers. Okay, even interline power flow controller, a series FACTS controller is called as a interline power flow controller. In that case, the controller, whatever we call it as, okay, is a controller that is unified if DC terminals are constant are connected of these two converters. If it is not connected, then you can take it as a in different control methods. Okay, simple control methods you can use. Okay, so unified you can call once this DC side of these converters are connected to each other. So that is about this one. And here in the first case we have discussed power flow in parallel path and also machine network, how complex the power flow in machine network we have seen, and the basic types of FACTS controllers including STATCOM, UPFC, SSC, and other thyristor controlled reactor, thyristor switched capacitors, thyristor switched series capacitors that we have seen, TSS, and all these okay, GTO controlled series capacitor we have seen, GSC, and all number of further study will have in the different later sections. Okay, so Here, dynamic stability considerations we have taken how the real power, reactive power flows, okay, how is controlled, and what are the parameters that, okay. Here we discuss the importance of controllable parameters. Here, different controllable parameters, we consider it as a x and a delta, x and delta. By changing x value, with this control parameter x value, we can control mainly the real power, and also by changing the delta, that is phase angle regulator or series compensator, we can change the real power flow through that one. And reactive power formula also we have seen there, the voltage magnitudes and phase angles are also changed. Once you, okay, we'll go to that point and we'll discuss. So the importance of controllable parameters we'll discuss, okay, in the next slide. Okay, see here you can see that by controlling the x value, the current flowing through that is controlled, and then finally the active power flow through that system will be controlled. And then by changing the phase angle control angle, that is a delta, we can change the again active power, because that is directly proportional to sine delta. Once delta is small, then it is proportional to, power is proportional to sine delta. And when delta is small, okay, then when delta is small, that is again proportional to delta. So by increasing or decreasing delta, you can control the real power flow through that one. Okay, it is directly proportional. By increasing delta, you can increase the power. By decreasing delta, you can decrease the power. But whereas the power flow is inversely proportional to x value, so by controlling the x value, we can change the reactive power. You can control the reactive power flow through the system. Okay, so that is the advantage. Then coming to the injection of the voltage. Okay, here in the case of if you want to change the reactive power, not only real power, power flow control means both the real power and also reactive power flow also, okay, on the transmission system. Both you have to control. How we control the real power? Real power is controlled by changing x value or delta value, and the reactive power is changed by injecting the voltage, which has control on the phase angle of the voltage. Okay, here only the in the once you inject the voltage in series and which is perpendicular to the current flow, then finally only active power flow is possible. But by controlling the voltage magnitude and also the phase angle, okay, you can see that the by injecting the voltage magnitude and controlling the phase angle of that injected voltage, or by current injecting the injected current phase and magnitude and phase angle, you can control active and also reactive power. In case of UPFC, we have seen that okay, the 360 degrees of control of magnitude is possible, and you can change the voltage magnitude from 0 to V maximum. That is the advantage of UPFC over the other devices. That means you can have control of real and reactive power by controlling the magnitude of the current and phase angle. Okay, by injecting the voltage, which is controllable magnitude and also the phase angle. Okay, and finally, series combination of series and shunt controllers will have the cost effective means of changing the real power flow and reactive power flow or control. Both are possible. Then actual today's topic will discuss many advantages are there with this fax technology. Yeah, actually, these fax technology used on the existing transmission system. So we need not go for the new transmission system. Whatever may be the existing transmission system, you can use that. Okay. In the case of uh, FACTS technology, you will have real and reactive power flow is possible. Mainly, we are controlling the active power flow through the transmission using by changing X value, delta value, and here in the loading capacity by connecting a FACTS controller in series, the loading capacity will be increased. For example, ideal compensator is connected at the midpoint, then it will double the capacity of the transmission line. Okay, that we'll discuss later in the shunt compensation. Then the security of the system increases, upgradation of lines are possible, loop flows are reduced, and we use the existing transmission capacity, existing lines, so that siting of new generation will be there, flexible. You can place at any point, even renewable energy technologies also will have advantages, because you can place a generation at any point, because you can increase the transmission loading capacity and also increase the power flows. Okay, and the reactive power flows are reduced, so that active power flow through the transmission line increases. Then utilization of interconnections are there, so utilization of low cost generation, okay, cheap power you can utilize, so that economically it is beneficial to use FACTS controllers. Then it provides a secure tie-line connection, thereby decreasing the overall reserve requirements of the system. Reserve requirements, extra capacity will be there only in the emergency conditions. We'll use this reserve capacity, so that by using these flexible AC transmission controllers, the capacity will be increased. So secure tie-line connections are possible, so that overall requirement of the reserve capacity generally will be reduced with this one. Further, while discussing about the different FACTS controllers, we'll discuss and stability. I have forgot. Okay, this one. Stability is also improved. In particular, the transient stability limit is increased by using the FACTS controllers. Transient stability limit, that is very important as per the FACTS controllers are concerned. Actually, use it for control of power, but parallelly it improves the stability. Okay, so these are the possible benefits of FACTS technology. And further later sections we will discuss about advantages. Again, one by one we'll discuss. Okay. Mm. Uh, so then we'll compare this with, already I told we have compared this with this HVDC technology, because both are competing technologies. Some places facts are useful, and some other places HVDCs are advantage. Okay, HVDC technology is advantage. And once you compare this one, the we use the facts technology on the existing system, so that the cost of the fact solution is lower than HVDC, because in the case of HVDC we require converters. The converters are used to convert the AC to DC, and then DC will be sent over the transmission. DC power will be sent, okay, and again at the receiving end we require to convert that DC to AC. So that converters cost and that transmission cost, if you consider, definitely it is not viable economically. HVDC is not viable for certain or for a short or medium transmission system. So only for very long transmission systems greater than 200 kilometers or 2000 kilometers, HVDC is viable. Otherwise, it is not advisable. So existing technology, fact solution is a cheaper one when compared to HVDC. And remember, HVDC is not a grid connect. Okay, it is not a grid network. You can connect, you can place these facts controllers at any point. Okay, at any place. Okay. But whereas HVDC you require a separate DC, so it is not separate link. So it is not a grid system. Okay, so it is only for long distances. This is advisable. Okay, or cables, overhead underground cables or submarine cables. this is HVDC is viable. Okay, then only HVDC is advisable once you have asynchronous grids, means with two different frequencies. Example, in future it may possible uh, to connect 50 head supply and 60 head supply to form wall grid. There, this HVDC technology is advisable. Otherwise, we generally generate, transmit, distribute, utilize only the AC at 50 hertz frequency in Asian countries, and only American countries they follow 60 hertz, and some of the European countries they have mixed, that is 50 hertz and 60 hertz. Okay, some countries